Hi everybody, I'm Priyanka. I'm a grad student at UC Santa Cruz, as already mentioned. So today I'll be talking about IO-efficient dynamic searchable encryption meets forward and backward privacy. So this is a joint work with Javad and Dimitrios from Hong Kong University and my advisor Ioannis. So let's motivate the problem a little bit. So in today's digital world, users use different kinds of online services, and for that they need to store their data online onto remote servers. But unfortunately, in the past, we have seen several data breaches that exposed sensitive user information from these servers. On top of that, service providers can also exploit users' data for their own profits. And to address that, several privacy regulation laws have been established. One effective way to protect users' data is by storing them in encrypted form, but then the user will lose the ability to perform queries like searches or updates on their data. Searchable encryption techniques are a really widely used ones which helps us to query on encrypted data. And this technique is also popularly known as encrypted search, and it has been adapted in many real-world applications. So what is searchable encryption? How does it work? So let's say the user or the client has lots of files with keywords in them, and they want to find those keywords later on. So they create an encrypted index and upload it to the server along with the encrypted files. Later on, while searching, they create an encrypted token and send it to the server, and the server will return the corresponding results back to the client. In dynamic searchable encryption, updates are also possible. That is, the client can upload new encrypted files and update the index accordingly. In this work, we focus on two aspects of DAC schemes, privacy and IO efficiency. The two de facto privacy guarantees that a DAC scheme should have are forward and backward privacy. And one of the most studied efficiency dimension for searchable encryption schemes is IO efficiency. So we can improve the efficiency of the schemes if we can improve locality and read efficiency if the data is stored on HDDs, and by improving page efficiency if the data is stored on SSDs. So several schemes have been proposed to make the DAC schemes forward and backward private, and another line of work focus on the IO efficient designs. Most of these IO efficient schemes are static except for the very last one in this list. So in the past, researchers claimed that achieving forward privacy along with IO efficiency is not possible, but our work bridges this gap. We present the first practical DAC schemes to achieve forward and backward privacy along with IO efficiency for both HDDs and SSDs. So what is forward privacy? It ensures that the server should not be able to relate an update with previous queries. For instance, let's say the client performs an update for the file F1 containing keyword cat, and then at timestamp 2, it performs a search for the keyword cat, and then at timestamp 3, it again performs an update for file F2, which again contains the keyword cat. Now, forward privacy will prevent the server to know that the update that is happening at timestamp 3 is for the same keyword that was searched and updated at timestamps 2 and 1 respectively. The high-level idea behind backward privacy is that the server should learn only controlled information about the deleted entries during search. I'll skip the details due to time constraint. So let's move on to locality and read efficiency, the two IO efficiency metrics for HDDs. Locality refers to the number of random disk head jumps when an operation is performed, and read efficiency refers to the number of memory locations read per result. For instance, here the client is searching for the keyword cat, and in order to retrieve the results, the disk head needs to perform 3 random jumps. So locality here is 3, and we achieve optimal read efficiency because we are reading only the entries corresponding to the results and nothing else. Whereas linearly scanning the entire index will achieve optimal locality, but worst case read efficiency. So Cash and Tesaro in their Eurocrypt 2014 paper already proved that achieving optimal locality and read efficiency along with optimal space is not possible. So in case of DSE schemes, during updates, if we can place the new entries adjacent to the old ones for the same keyword as shown in the picture, will improve locality, but then the server can infer that these two entries are related, and that will violate forward privacy. Similarly, let's first briefly see what page efficiency for SSDs is. It basically means the ratio of number of pages retrieved for encrypted results to plain text result. For page efficiency, also we can improve it if we can store the entries for the same keyword in the same page, but that again violates forward privacy, similarly to the case we just saw for HDDs. So now we have seen these definitions, and we also have an idea why forward privacy was thought to be incompatible with I/O efficiency. Now we can move on to our contributions. So we present two families of DSE schemes, which are forward, backward, private, and I/O efficient, and they perform better asymptotically and experimentally than the state-of-the-art non-I/O efficient DSE schemes. So our starting point was SDA, which was presented in NDSS 2020, and it's basically a static to dynamic compiler, meaning that it converts any static scheme to a dynamic one, maintaining forward and backward privacy. So the high-level idea is that the client creates an index of size 1 whenever an update happens using the underlying static scheme and upload it to the server. And whenever two indexes of same size exist at the server side, they are downloaded, decrypted, and merged together to create an index of size, double the size, and uploaded back to the server. So in this way, with SDA, for n updates, up to login indexes are created. And as I said, SDA transforms any static scheme to a dynamic one. So if we instantiate SDA with one of the static I/O efficient schemes from this list, we get what we wanted. That is, we achieve a DSE scheme with I/O efficiency and forward-backward privacy. But SDA has an issue, that is, SDA's updates are amortized. Some of the updates are very efficient, takes constant time, whereas some of the updates can be really costly because of the merges that happen at the client side. So to resolve that, we went back to the same paper, which presents another framework, which is called SDD, which again converts a static scheme to a dynamic one, but it has de-amortized update cost. But it does not serve our purpose because instantiating SDD with I/O efficient schemes will violate forward privacy. To understand how, let's just briefly see how it works. So now we have 4 indexes per index level instead of 1, namely new, old, older, and oldest. And whenever an update occurs, it is stored in new 0. And whenever new index of any index level is full, their entries are moved to one of the empty old indexes. And whenever oldest and older of any index level is full, they're merged together and moved to the new index of the next index level. So basically everything boils down to, again, merging 2 equal sized indexes and creating an index of double the size. So in the original STD, they used oblivious maps or OMAPs to perform these merges. So basically, they store some metadata like keyword frequency to know where to store the entries in the new index. So how SDD violates forward privacy when it's instantiated with I/O efficient SE schemes? To understand that, let's choose one of the schemes from this list, one-choice allocation. So in one-choice allocation, the database is visualized as an array of bins, and entries for the same keyword are stored in adjacent bins, and so that during search, all the adjacent bins can be read with locality 1, and also bins are filled up with dummy entries if they are already not full. Here, the gray entries here are the dummy entries. And also for simplicity, let's just omit the file identifiers. So in one-choice allocation, like any other I/O efficient schemes, the placement of the entries is a direct function of their values. So if we use one choice allocation and move the entries from oldest and older one by one and place them in the new index, the server can infer as soon as we place the second cat keyword in the third bin that it's related to the entry that is already present in the second bin, and that will violate forward privacy. So in order to solve that, we replaced this OMAPs with a new protocol called oblivious-merge, which also performs asymptotically better. So with this oblivious-merge, we achieve our IO efficient framework called LSTD. So basically, oblivious-merge merges two equal-sized indexes in locality-aware manner. So let's see how it works in a very high level. So first, everything from oldest and older indexes will be copied into a buffer, and then the buffer will be sorted obliviously with respect to the lexicographic order of the keywords, and then each of the entries will be assigned a bin tag, and then we will add extra dummy entries up to the maximum capacity of each bin, which is 3 here, because we don't want to reveal how many real or dummy entries each bin has. So then everything will be again obliviously sorted, this time with respect to the bit tags. So everything belonging to the same bin will come together, but then every bin is now assigned more elements than they can hold. So another linear scan will be performed to tag the elements that we want to discard. The dummy elements are marked here with the red infinity tag. So another order preserving oblivious sort will be performed to push all the elements we want to discard at the end, and then they will be discarded. So remaining elements will be grouped into sets of 3 and moved to their designated bins. So in oblivious-merge, in every step, we are either performing oblivious sort or linear scan. Neither of these operations reveal any information regarding the keywords order, quantity, or relations between them to the server. So we basically implemented the IO efficient schemes from these 2 papers, namely one choice allocation, two choice allocation, nlog n, and several of their variants, and instantiated them with our LSTD framework. We performed several optimizations for each of these schemes to work with our oblivious-merge framework. We didn't implement the rest of the schemes from the green bubble because mostly they are theoretical, and we also believe that with some modifications to the oblivious-merge framework, it will work with other IO-efficient static schemes as well. So finally, we did lots of experiments. We tested our IO-efficient LSTD and SDA framework with we compared them with the original non-IO efficient STD and SDA, and our results show that our schemes perform up to 1,000 times better on HDDs and up to 300 times better on SSDs for search time, and you do better asymptotics. They perform a bit better on RAM as well. And we did our experiments on various settings like variable result size, DB size, cache, with both synthetic and real data set, and with various practical scenarios. So with that, I would bring back the same slide for you to look. And thank you, and if you have any questions.